Hi. In this video, we're going to look at scalar projections. We're also going to take a brief look at vector projections, but we'll save the calculations of those into the next video. So let's start with looking at an example of scalar and vector projections. Down the bottom here, I've got a box on a horizontal surface. Let's say we want to pull the box, right? We're going to apply some force to the box. So we can represent that with a vector. If I had a vector this long, we would pull the box at some rate. If I had a longer vector, then we would pull the box faster. Let's say I pulled the box, but I didn't pull it parallel with the ground it was resting on. Let's say I pulled it at some elevation. So we'll represent it by this vector here. Now, we're not pulling hard enough to actually lift the box off the ground in this example. It's still going to move along the horizontal surface, but how much is it going to move? What's the rate going to be like compared to these horizontal vectors down below? It turns out that the amount that it's going to move, or the rate that it's going to move, is proportional to the component that's pointing in the direction of motion. So if I draw down here, and this is a right angle, then the rate of motion is going to be proportional to this vector here if we ignore things like friction and such. This vector that I've drawn here is what we call a vector projection. The length of that vector, so if we're just considering the length only, so this length, we call the scalar projection. Scalar because it's not a vector, it's just a length, it's a quantity, it's just a number. Projection, it sort of refers to sort of a light projection, right? So you can visualize this as some light source up here shining down on the vector. If this vector was an actual physical object that could cast shadows, this is going to be the length of the shadow, right? So this is what we call the scalar projection. If we imagine that as a vector pointing in that direction, it's a vector projection. So let's have a look at a couple of these things without an application, just with the vectors themselves. So I will draw a couple of vectors up here. Let's call this vector B and vector C. So we're going to look at scalar projections in this video. So the scalar projection of B on C is if we have some dots coming down here at a right angle, and we are looking at this length. The way I like to notate this, a lot of people do different things, but I like to call it P for projection of B on C. So that's a projection of B on C, is this length. If we have a look a little bit higher, it's the adjacent side of this triangle if we're considering the angle between the two vectors. So if I want to calculate the length of that adjacent side, we've got cos theta equals adjacent on hypotenuse. We want the adjacent side. Our adjacent side is notated this way. It's our projection of B onto C. So A equals projection of B onto C. Our hypotenuse, this guy here, is just the length of that vector, which is our magnitude of B. And this is our formula for the projection of one vector onto another. So the projection of B on C, we find the magnitude of B, we times it by cosine of the angle between the two vectors, and we get our adjacent length, or our projection of B onto C. Now, for these things, one vector does not need to be horizontal. You could have something that looks a little bit different. And let me do some erasing for some space. So if I had two vectors that look like this, Let's call these some different vectors. So this can be D and this can be E. If I was looking for the projection of D on E, then all I'm doing is I'm drawing a dotted line that's right angles. And this length here is the projection of D on E. So this refers to this length here. The projection doesn't even need to be as long as this vector. It can be shorter than the vector. So if I was to draw, let me do another one just so it's very clear. If I was to draw my two vectors again, and this one was short, let's call them F and G. If I was to look for the projection of F on G, then again, I can imagine this line extending out. I'm drawing a dotted line that's at right angles down to it. And this length here is my projection of F onto G. So the projection may be bigger than the vector itself. It's not a physical projection, so we don't need the physical shadow to actually fall on this vector. It's just this sort of hypothetical shadow that forms in the direction of the vector. That length is what we call our scalar projection. So let's have a look at calculating a few examples. I'll do some erasing work first. Oops. Okay. And we'll zoom back in. All right, so we have two vectors on this plane. We'll do one that is 4 units in length along the x direction. Let's do another one that is 3 and is 4 up, like this. We will call this A, and we can call the other one B. We want to determine the projection of A onto B. There's also an angle between them. Let's call it theta. Theta in this case equals, let me just work it out. I think it's a number, but I'll just make sure. So the angle between them is 53.13 degrees. So that'll be given in the question. We're looking for the projection. So the projection of A on B, our formula, is magnitude of A times cosine of the angle between them. My magnitude of A, you can see that this triangle here, it's 3 across, 4 up, so the hypotenuse is going to be 5, our 3, 4, 5 triangle. So we've got a magnitude of 5 cos of 53.13. If I pop that into my calculator, with this is actually a recurring decimal, but we'll get something very close to 3 in length. And you can see if I draw my dotted line coming straight down to it, you can see that's exactly 3 in length down here. So that's the projection of A onto B. We can also do the projection of B onto A, like this. So let me clean up this diagram. If I was to do that, we've got here and here. If I was to do the projection of B onto A, what I'm looking at is this length here. That's my scalar projection of B onto A. Now, if I was to guess how long that is, I would say it's about maybe 2.5. So I'm going to guess it's approximately 2.5, but let's calculate what it is. So the formula is going to be B cos theta. The length of B is 4. Cos 53.13. Pop it into our calculator. 4 cos equals, and we get 2.4. So about 2.5. I find when doing these questions, it is a really good practice at your stage to estimate what you think the projection length will be. The reason for that is it gives you a geometric intuition for what's going on, and these problems are going to get progressively more involved. So if you can develop that intuition, the geometric intuition, it'll probably hold you in better stead down the line. So what we've looked at is the scalar projection. If we're given two vectors, if we're looking for P of A on B, all we need to find is the magnitude of A, the angle between it, and we can work out what this length is of the adjacent side of that right angled triangle. That's the video. I hope you enjoyed it, and I'll see you for the next one. This video accompanies a worksheet series that aims to develop conceptual understanding with vectors. If you'd like to access the worksheet, click in the description below.